All right, this is Mr. Gillum, and today we are going to be talking about medians and altitudes of triangles. And so what we're actually shooting for here is for you to be able to construct a centroid and an orthocenter. So we got two new vocab words of things that have to do with triangles, kind of like the circumcenter and the incenter, but now we're going to find the centroid and the orthocenter, and we're going to learn about medians and altitudes. So here we go. Let's take a look. A segment that joins a vertex of a triangle and the midpoint of the opposite side is called the median. All right. So basically what we need to do is we need to make sure that we know how to find the middle of a segment. And we do know how to do that because when we were doing perpendicular bisectors, we knew that it bisected the segment. So what we're going to do to find that median is just simply construct a perpendicular bisector, but instead of actually drawing the line for the bisector, we're just going to mark where the midpoint is, or the we call it the median. The median. So it's halfway in between each end of the segment. The centroid is the point of concurrency of the three medians. It's always inside the triangle, even no matter what. So for instance, this line right here is not necessarily perpendicular to this segment over here. Okay, it is though, however, right in the middle. This is exactly equal on both sides. All right, and that's the only thing. It doesn't say anything special about the angles. These angles can still be different. This is right in the center. These angles can be different, and that's it. It doesn't have to be perpendicular or anything like that. Same with this guy. Okay, it's right in the center, but it doesn't mean that they're perpendicular on each side, or that they're equal, or these angles are equal. Nothing special like that. Just that it connects the midpoint, or sorry, the median is connecting the middle of the segment to the vertex across. So there is a theorem that goes with this. All right, and we're going to get that in a second, but first I want to explain how to find it, and I just kind of did verbally. But when we're finding the median, we're going to take all the steps that we take to find the perpendicular bisector. So we're going to open our compass to a width that's a little bit bigger than halfway over the segment, and we're going to make our first arc, and we're going to put the point on the other side of the segment. And we're going to make another arc, keeping the width of the compass at the same. And where those two arcs intersect, if we connected those points, that would be the perpendicular bisector. But in this case, we're not finding the perpendicular bisector. We just want to find where it is bisected. So when I get my straight edge out here, I'm just going to draw a dashed line because we don't actually want the perpendicular bisector. We just want to see where it crosses. So I'm going to connect those just like it were a perpendicular bisector. But the only point that I'm actually concerned with is this point right here in the middle, the median. Okay, that's called the median. And the median connects the middle of that segment to the vertex straight across from it. And so we take that point. Oh, it's taking forever. And it's taking me forever. And it's taking me a really long time. And I connect that point to the vertex of the triangle straight across from it. And that is the median right there, that line. Okay, it touches the middle of the segment here, and it goes right through the vertex. That's the median. All right, the centroid theorem. Okay, so after you do each one of those medians, each of these median lines, you get that centroid dealy. All right, and that centroid has a special property about it. Okay, it's got a ratio, and the ratio is this: 1/3 of the length of the segment of the median is in between the centroid and the segment, and 2/3 of it is in between the angle and the centroid. All right, so same way here. So 1/3 of this length of this median and 2/3. 1/3 and 2/3. All right, so we could get into some examples, and that's what we're going to eventually end up doing in class. But if I said that this entire length of this median was 9, then I would know that the length of CO would be 6, and the length of OD would be 3. All right, or I could even say something like this. I could say, if this guy is, let's just make him, we'll say 8. If this length from O to B is 8, then I know for sure if this is a centroid that this length would be 4. 4 and 8 make 12, 4 is 1/3 of 12, and 8 is 2/3 of 12. All right, so this is the centroid theorem. It's 2/3 the distance from the vertex to the midpoint of the opposite side. So when we want to construct a perpendicular line through a point not on the line, we're going to use this information in a second to make the orthocenter. So now we have done some constructions with making perpendicular lines, but specifically today we need to make a perpendicular line through the vertex of the triangle across from its segment. So this is going to be a little new construction, okay? And I'm going to talk you through as the tutorial goes here. I'm going to start with putting my point on point P, or whatever point it is. In this case, we're going to use a triangle point, the vertex of a triangle. And I'm going to draw an arc that crosses over the segment twice. And it's going to be important that it crosses over twice. So I've drawn the segment, and it's got a point right here of intersection and a point right here of intersection of this line that I'm drawing this perpendicular line through. Okay? And the next thing I'm going to do is I'm going to take the point of my compass, and I'm going to put it on its first line of intersection. And I'm going to make an arc out here in the blank space somewhere, okay? And I'm not just going to do that once, I'm going to do it twice. So I'm going to make that arc right here somewhere. There it goes, and then I'm going to do the same thing again with this point. I'm going to move it over here to point A. I'm going to make the same exact arc, not moving my compass. Now, it looks exactly like the marks that we should have on our compass for or our constructions for a perpendicular line, same exact arc markings. So now it's just a little different how we constructed it. Okay, so we got point P, and we made a perfectly right angle with segment AB, or line AB, or it cuts off. It's hard to tell what type of ray or segment or line it is. But this is actually a 90-degree angle right here. So one more time, I'll show you again. The first thing we're doing is we're starting with our point on the point that we want to draw it through. We're going to open our arc, and we're going to swing it around and make sure that it crosses twice. We're going to take our point, and we're going to make a new arc out here on both of them. And once we have that, we just draw our line through our point right here. And wherever it crosses, that's going to be a 90-degree angle. So that's going to help us to construct an orthocenter, okay, and an altitude. The altitude of a triangle is a segment from the vertex to the opposite side, but it has to make a 90-degree angle. It has to make a 90-degree angle. So there's special things that happen here with this altitude. So of course we'd put our point here, and we'd swing it across, and then we'd swing it, and then we'd connect, and so we'd have a perpendicular line. Where all these altitudes cross, and we're just going to have to really get familiar with that vocab, altitude, where it makes a 90-degree angle with the angle and its opposite side. These angles aren't necessarily equal by any means. The only thing that this altitude guarantees is that I have a perpendicular line from this opposite segment to its vertex. Okay, that's all it guarantees. The orthocenter is where all of them intersect, or where they're concurrent. Okay, so we've learned some new vocabulary today. We have the centroid, where we just connect the vertex to the middle, and that's where they cross. And we now have the orthocenter, where we draw perpendicular lines across. However, on an altitude, when I'm making an altitude and trying to find an orthocenter, it's not always on the inside. On a centroid, it will always be on the inside, but an orthocenter, it will not always be on the inside. If it's an acute angle, it will be. It'll be on the inside and it'll cross. But if it's a right triangle, then it'll be actually right exactly on the right angle itself. If I had a right triangle, oops, got a nice right triangle here. Okay, there's my right angle. The right angle with its opposite side would actually be right on this point. And the opposite side to him would be right there. Its right angle would actually be on this point. So on a right angle, the orthocenter is actually on the right angle itself, whatever point that is. So if this is D, E, F, the orthocenter of this thing would be right at E. And an obtuse triangle, even. Okay, we're going to experiment with this in class. We're going to call this obtuse right here. The right angle of this guy, with this guy, we'd have to actually extend the line. It'd be right here. Okay, and we actually have to extend it a couple different ways. This guy, its right angle would be right there. And so the orthocenter would actually be outside the triangle. Right there. So there you go. So the orthocenter, I need a perpendicular line through the vertex to its opposite side. With the centroid, I just need to find the median and draw lines to it. So new vocab, new constructions, kind of, and that's what I want you to know for tomorrow. I want you to know about the centroid and the orthocenter. Don't forget the altitude. I didn't say that word very often. The altitude is when you connect the vertex of a triangle to its opposite side using a perpendicular line. And finally, the centroid is where you're looking for the middle part of this segment, and similar construction to the perpendicular bisector, but you're connecting that to the vertex actually. So that's it for